Okay, so we are we're going to do the last bit of new material today before the test, and then the test will be a week from today. So Wednesday we'll review for the test. Everybody got it? All right. So last time we did section 4.7, which was quadratic regression. So today we will do 4.8 and 4.9, which is 4.8 is about interaction. And I've hinted at action a couple of times, but today we'll formalize it and get some examples about how to deal with it. So let me pull up the first example. And this is straight out of the book. Oops, that's the wrong program. There. So this is about advertising for a... I guess I have to turn it on. For Bonner Foods. So this is one of the examples that they go through in the book. It's made up data, but it's made up with a purpose, and it is very good at showing what we want to see about interaction. So the idea here is this company is trying to decide how much money to spend on advertising, and also where to put that money in advertising. So they have radio and TV ads, and then they have print ads. So that's magazines, newspapers, things like that. All right? So something happened. Oh, my live name was off slightly, so I think if I just do that should fix it. Yeah. So here's the data. They have region, so this is like region of the country, and then discrete variables for radio, TV, and print. So they're just discrete representations of certain ranges of dollar amounts that they're going to spend on the advertising. And then volume is their sales volume for those regions. So in the different regions, they use different combinations of these radio and TV dollar amounts. Got it? So let's go to this region and spend this much, then we'll compare the sales in that region to other regions that get different amounts of sales. Okay? So there's the data. Let's. I'll come back to that. That's a variable that I created myself. If I do a quick plot of this data, what do you see? The correct answer is nothing. It just looks kind of like a shotgun blast. Remember, we have discrete levels of our x variable, so everything is in these vertical lines. But you do see that it's going up a little bit. So as you spend more, and I have to scroll, I guess, to even see the which variable got plotted. That's the radio TV. So as you spend more on radio TV, you do see there's some increase, but there's a lot of variability. If I plot now by each level, so my plot statement says volume by radio TV but equal print, it says give me a separate line on the graph for each level of print advertising. All right, so it had 5 levels as well. So if I run, I don't know why this is. That's even worse. I don't know why it's making me scroll to see the whole thing. Usually it just fills this whatever it has available. But anyway, I scrolled down so we can see the legend here. So for each level of print, 1, 2, 3, 4, and 5, we get a different line. It's fitting a linear regression for radio TV as the explanatory variable and volume as the dependent variable, the response variable, but for each level of print. What do you notice?
Seems like the bottom one has the biggest slope.
Okay, the bottom one has the biggest slope. Well, that's when print is at a minimum, right? That's when you're putting the least amount of money into print ads. Then you get a steeper line for your radio ads. What is that saying?
Radio has a better advertising.
It's not, no, that's,
Print's not good.
it's that when you're not spending much on print, then putting more into radio and TV has a bigger bang for the buck, right? It has a steeper line. But at the top, when I'm putting a whole bunch into print advertising, then increasing my radio and TV time doesn't change that much. So the fact that these 5 lines have different slopes, and it's really the middle 3 are about the same slope, but the first one and the last one have very different slopes. That's called interaction. Now, interaction means, in a statistical sense, that the rate of change of one variable depends on what level of the other variable you're at, meaning my 2 x variables. So the rate of change of y with respect to one of my x variables changes at different levels of the other x variable. Then those 2 variables are said to interact. There's interaction between them. If all these lines were parallel, then it wouldn't matter how much you spent on print. You still get the same return on investment for radio. You get the same slope. Rate of change of volume with unit change of radio and TV ad. Right? So this is interaction. Let's look at another example.
That was the amount put together variable, right? The rate of change depends on the amount.
Right, the amount of the other variable. That's right. Well, I'm going to have to do the old-fashioned opened here. Well, for some reason, I don't know if I left it open on my computer upstairs, but it didn't have my my SAS program that I ran. I hope I didn't wipe it out. Does anybody see one here that says something about interaction? Maybe it's up one more from this. There, interaction example. I put it in the wrong spot. Sorry about that. Okay, so I'm going to run a data step here that's going to just simulate some data. I'm going to run that, and then I've got 2 x variables, x1 and x2, and then a y variable. So here's 2 plots. This is x2. Here is x1. Okay, same kind of thing where we have discrete values, but if I plot y by x1, so I have to scroll to see the axis. I wish there was a way to... There we go. There, I zoomed it out a little bit. So you can see the x1 variable, 1 to 5. If I ignore the other variable, x2, what do you notice about this plot? There's very clearly something going on, but there's only one line, and it seems to be going through the middle cloud of points, right? But for each value of x1, my y variable has 3 distinct groups. And that's because there's this other variable kind of lurking behind the scenes, right? But if I ignore that other variable and I plot it, this is what the plot looks like, and here's the line of best fit, right, through those points. If I scroll down now to look at the other variable, then it's at 3 levels, 10, 20, and 30, and my y, there's clearly a downward slope across those points, right? So both of those variables have what we call a main effect, that all by themselves there is a trend across those variables, right? If I look at an interaction plot, which shows both variables together, with one of them being like in that adds one, this is x1, but a separate fit for each of the values of x2. Do you see any interaction? Does the rate of change with respect to x1 depend on which x2 value you're on? They look pretty parallel. So I see no interaction. There's not an interaction between those two variables. Okay? Well, let's go back up and rerun the data set. And I don't want you to even know what I'm doing right now, but I'm going to come back and tell you here in a little bit. So I changed the value of a parameter there, and then I reran it, and this was the plot, right, that I was using? Now what do you see?
Interaction.
Now there's definite interaction. When x2 is at 10, it's the black circles. You have this much rate of change of y with respect to x1. Not very, very steep slope, but it gets steeper as you go up in value for x2. So at the highest level of 30, you have your steepest line. So the rate of change of y with respect to x1 depends on which value you're on. Right? Now, I was playing around with a three-dimensional plot. And if you only have 2 x variables, then you can do a three-dimensional plot. If you have more than that, then you can't do it. Okay, it went away. So this is what we call a response surface. Right? So I have a grid of points for my x1 variable. So that's in this axis. And then my x2 variable. And then my y variable is the vertical axis. Right? Remember Calc 3, you had to do this kind of stuff? So what does that look like? A plane. It looks like a plane, right? Can you see where there's interaction in this plot? It's not real obvious. I was hoping it would be more obvious, but
Is that when the line bulges?
it's not where it bulges. That's just random noise. But look at the slope of this line compared to the slope of this line. And then this one, right? The plane is tilting more as you go across the x2 values. Right? So the plane is not the edge of the plane. You can see it right at the edge here. The edge of the plane not parallel with this x2 axis. If it was, you would have no interaction. Right? So the plane is off kilter. So that's how you see it in these three-dimensional graphs for that kind of interaction. There's lots of other kinds of interaction. If you could have one line that's perfectly flat and then another one that's real steep, another one goes the other way. You know, it's not always a plane that's being tilted. It could have a hump in it or whatever. Still interaction. It's just if the relationship between one variable and y changes when you change the value of a second variable or a third or whatever, then that's called interaction. Okay, so now how do we model this? Let's go back to the Bonner Foods data. And if I fit, well, I guess let's hold off on running an analysis until we get some theory out of the way. Let's model it with Greek letters. If y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. Right? That gives me, and I'm suppressing subscripts that get in the way here. Right? And I don't have an error term, so I can put a hat on there to justify that.
Quick sort of back step. This is a linear.
This is a linear model. Yep, it's a linear model. It's linear in the parameters. Okay, so remember my x2 variable was a discrete random variable and it had values that went from 1 to 5. So what is the model when x2 is equal to 1? Okay, y hat equal beta 0 plus beta 1 x1 plus beta 2. And I'm going to go ahead and put in beta 2 times 1. Right? I'm just plugging a 1 in for my x2 variable. So simplifying, I get beta 0 plus beta 2 quantity plus beta 1 x1. Okay, so this is x2 equal 1. x2 equal 2. What do you get? Okay, you get the same looking thing, but 2 beta 2 plus beta 1 x1. What do you get when you go 3 and then 4 and then 5? If I plug a 5 into x2, I get 5 beta 2 plus beta 0. Now why am I grouping those together? They're just the constant part of it. So this represents what? The intercept of the line when x2 is a 1. This is the intercept of the line when x2 is a 2. And if I have a 5, then the intercept of the line is beta 0 plus 5 beta 2 plus beta 1 x1. Now, does that fit the data? There was the data. What this says is this model at different values of x1 changes the intercept of the line for each x1 value. But it does not change the slope. Does that fit? Do the intercepts change? Yeah, they definitely change. This one has an intercept. Actually, this is a 1, so here's 0. So this intercept's about here, this one's about here, and so on. So the intercepts do change. But the slopes also change. This model does not allow for different slopes, which is fine if there's no interaction. Right? We said if the slopes are the same, there's no interaction. I don't need to model. I don't need my model to be allowed to change the slope. But if there is interaction, I need to modify this model in some way that will let the slopes change as well as the intercepts change. Any ideas? I need this beta 1, or then I don't want to say beta 1. I need this coefficient of x1 to change when x2 changes also. Right? The intercept value changed when x2 changed, but the slope parameter did not. How can I set the model up so that the slope parameter will also change? Modify this model for me. We need to add another term. I'm not sure whether you'd be able to just figure it out by looking at it, but I kind of think you might be able to. Okay, plus beta 3 times what? I can't add a third variable. I only got 2 x variables. If I make it x1, you're doing what I want you to do. You're thinking it through. If I make it x1, then changing x2, the slope would be beta 1 plus beta 3, no matter what x2 was, right? But I do need an x1 on it so that it's a slope parameter and not a constant. See, when I don't have an x1 here, plugging a value in makes this become part of the constant. But I got to make this change when x2 changes. X1, x2. The product of those two. Now, do what we did over here. Let x2 equal 1. Y hat is equal to what?
Plus beta 2 plus
Okay, go ahead and do it the way you're saying it. 1 times 1. Right? Everybody follow me? I plugged a 1 in everywhere I had an x2. This one I already grouped over there because we did it before. You knew how that worked. But what about this? Factor out an x1 and I get intercept of beta 0 plus beta 2 and a slope of beta 1 plus beta 3. Now this particular data set does not have x2 ever equaling 0, but if x2 equaled 0, what would I get? This term would drop out, this term would drop out, and I'd have beta 0 plus beta 1, x1. Right? Then as x becomes 1, I add something to the intercept, and I add something to the slope. So the intercept changes and the slope changes. What's x2 equal 2? What's that model?
beta 0 plus beta 2 plus 2 times 1, or 2x1 times 1.
It's beta 0 plus 2 beta 2.
Plus
So the intercept changed. Plus
beta 1 plus beta 3 times x1. Like 2. Oh, plus 2.
Oops, I put a
2 beta 3.
plus 2 beta 3 x1. dot, 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 till x2 is a 5. And we have beta 0 plus 5 beta 2 plus beta 1 plus 5 beta 3 x0. So you see that for any level of x2, the intercept changes and the slope changes. So what is this interpretation of that parameter? What is beta 3? What did you say, Kevin?
Interaction parameter.
It is the interaction parameter. What's the interpretation of it? This beta 1 is excuse me. I get that thing where you can't talk for a little while. This beta 1 is the rate of change of y with respect to x1 holding x2 fixed. All right? Give me that kind of an interpretation for beta 3.
Beta 3 is the rate of change with both x variables.
Okay, almost. It's the rate of change as both x variables change. But another way to say that, maybe a little cleaner.
As in, it's the rate of change of beta 1?
Yeah, and what's beta 1? The rate of change. It's the rate of change of the rate of change. But that's what it is. It's how does the slope change? Slopes are rates of change. So it's the change in the slope, right? So it's a rate of change of the rate of change. So it's the, let's say it easier than that, it's the change in the slope of x1 relative to x2. So how much does the slope change as I change x2? Okay. So that is called the interaction parameter. So in our model, that, our full multiple linear regression model, we have all these betas in there, and each beta can be tested separately. So if I test beta 1, I'm testing to see if beta 1 is 0. I'm testing to see if the rate of change of x1 holding x2 fixed is 0 or not. Right? Is there a change? When I test beta 3, I'm saying, does the slope change as I allow x2 to change? Does the slope with respect to x1 change as I allow x2 to change? If the answer is no, it doesn't, I fail to reject the null hypothesis that beta 3 is 0, then I say, well, there's no interaction. But if the null hypothesis beta 3 equals 0 is rejected, then I'm saying, yeah, these slopes are not the same. As I go across the different models, the slopes change because beta 3 is not 0. If beta 3 is 0, I don't reject my null hypothesis, then this term drops out. And I have a model with no interaction. The model with no interaction allows the intercept to change, but not the slope to change. Interaction is difference in slopes, which is exactly what we saw visually with our eyes. When they were the same, they were parallel lines, we said, oh, there's no interaction. The slope is the same, doesn't depend on the value of x2. Okay? So how do we do this inference? How do we do this test? I'm going to run SAS. Okay? But we also need to know what SAS is doing, but let's do that first. Let's go to the to the Bonner data here. And I'm going to...
Pull that to the right.
Oh, yeah. What I'm going to do is I'm going to run a proc-reg that has my y variable equal to x1. Oh, wait. Radio was x2. No, I don't know. Doesn't matter. So each... I'm going to do just the first variable, and then both variables, but no interaction term, and then both variables with an interaction term. So what is this rad by print? Well, rad for radio, not for radical. So it's rad by print. So it's the interaction. So where do I get that variable? Well, what is it in the model we derived? It's x1 times x2. So rad by print is radio TV times print. And I can do that in a SAS data step. I could do it in Excel before I read it in if I don't like using SAS code. But whatever, I need a product of those two variables. And that's my interaction variable that I'm going to add into the model. Okay? So it's already in there. Let's run those 3 regression models. And actually, I'm going to go ahead and I started to say I'm going to turn off the ODS graphics so I don't get all those extra plots. But they're actually kind of interesting here. So first thing I'm going to do is I'm going to clear out all this stuff. Which makes it run slow, so we have to sit and watch the little hourglass for a while. And I have to tell a joke or two. And then eventually, hopefully before I have grandkids, oh, there it is. All right. So now I'm going to go to the top, and we'll work our way back down. Here's the model with just the radio TV variable. What's your conclusion from this model?
Beta 3 is 0.
I don't have beta 3 in this model. All I have is radio TV, which is my beta 1.
So there's a chance that beta 1 is 0.
There's not enough evidence to reject it all.
There's not enough. It's really close, but it's not statistically significant. But it's really close. I wouldn't throw it away completely, but I'd say, we maybe need more data. What about R squared?
It's terrible.
It's not very good at all, right? So what this test is a test of the model in general, which is also you can think of as a test of whether R squared is 0 or not. So we can't reject that R squared is 0. It's maybe not helping at all.
So why is that p-value the same as the radio TV variable?
That's a good question. We've been through this, but it's been a while. Why is this equal to this?
Because that's is that saying the interaction like between the change in your radio TV?
I have no interaction. Remember I ran 3 different models? This model only has radio TV in it. And that's the hint. Why is this one equal to this one? Because there's only one variable. And so the degrees of freedom for model is 1. The degrees of freedom for radio is 1. And this is the t squared equals the f when there's only one variable. As soon as we add the second variable, which by the way here is the residual plot for this model, and here's the fit plot. What does fit plot mean? Well, it just means here's the line of best fit with my confidence bands and my prediction bands around it. And you see why R squared is so small, right? There's a lot of random noise around this line if I ignore the other variable. But when I fit the other variable, if I fit with no interaction, I'm forcing the slopes to all be the same, but I'm still going to explain a lot more of the variation in y with that other variable. So my R squared should shoot way up. This is what I would call the main effect of x1, of radio. When I x2 into the model, there's the model. So now look what happens to R squared. So x2 is really important to this model. But also, what happens to radio when I control for the print? It becomes not only significant, but highly significant. Right? So before, there was just, without accounting for x2, there was too much random scatter around the line. Well, now I get to fit a different line, so the scatter around each of those lines goes way down. So my R squared goes up, and I'm going to start the sentence over. Instead of saying if, R squared goes up. But if the random scatter around the model now has gone down, my sum of squared errors went way down, right? Which means my mean squared error went way down. Right? How is this standard error computed? How is this, right? How is this F computed? You're dividing by the mean squared error, right? The root mean squared error is part of the standard error here. So if I made it get really small compared to what it was before, then I have a lot more power to detect differences. So this became very significant, whereas before it was not. Okay, now, the one with interaction in it. Oh, I got some plots to look at. Now I get residual by regressors for volume. So here's my radio TV residual plot. Here's my print residual plot. But I don't have a way to look at them together. Right? I have to do them separate. Both of them don't look all that great. Right? But it's not automatically printed out here, but you can ask for a residual plot of predicted versus the actual Y value instead of the X values. So then you'd see it's pretty tight. Now let's add interaction. And you don't get that fit plot when you have more than one X variable in your model. SAS won't give you a fit plot. There is a way to get it with a different procedure, which I'll show you here in a little bit. But here is the model with interaction in it. R squared. Even better, right? Now what do you know about R squared if you put another X variable into the model? It goes up. It's guaranteed to go up even if that variable is not important. So even the new variable here is the interaction, the product variable, right? So even if that didn't help, the R squared is still going to go up some. And it went up from about 0.96 to 0.98. Was that a significant improvement? Yep. It says right here that the interaction radio by print term is highly significant. Now, interpret its value for me. Negative 0.35 if I round to two places. What is that saying?
Rate of change
Of the
beta 1.
Of beta 1. Right. So as radio, no, print's the second variable, right? So as print increases, the slope of the radio TV decreases by about this much per unit change in X. Right? So it's going down about 0.35 every time I increase my print budget by 1 unit. Right? Then again, I don't get great results here, but let's go to maybe I didn't do it with this particular example, but it's real quick to do. I'm in the wrong program. No wonder. I don't have it here either. Let's run this same model but I'm going to use proc GLM instead of proc reg. And GLM stands for General Linear Model. Right? It will run regression models just like it's done. It parameterizes them slightly differently. And I'm not going to go there with you in this class. It's not a big deal, but it will also run ANOVA models where you have classification variables, not numeric X variables. Maybe you have categorical X variables or whatever. It'll handle that situation, right? So it'll run anything that regression will run. It looks different. The output looks different. But let's go ahead and run it. I'm just going to copy this model statement. So the only thing I'm changing is, no, I'm sorry, I'm not. Another thing that it lets me do is take the product of my two variables as an interaction right in the model statement, whereas proc reg will not allow that. If I put this into proc reg, radio TV times print, it'll say, I don't know what that means. That's a syntax error. So you have to create the product, give it a variable name, and put it into proc reg. But proc GLM lets you just do this.
So is there a difference between the two, though? Because that'll just plot it.
Well, I'll show you. And I'm going to put in here, I'm not sure that I have to with this new version. Well, actually, let me try and run it without it. But I was going to put an option that says solution. Give me the solution to the regression equation. Because GLM, at least used to, wouldn't automatically give you that. Ooh, look at that, a contour plot. So that shows interaction, although, has anybody ever learned how to read a topographical map? Yeah. You're in the Boy Scouts, right? Yeah, that's where you learn that. That's what a contour plot is, right? When you only have two X variables, right? If you have more than that, it gets more confusing, but it's still the same idea. But so these are, you can see that things aren't changing in a linear way. There must be some interaction going on. It's curved rather than straight linear. But here is the output. I was thinking it would give me a fit plot, but it didn't. Here is the output. So top part is identical. I don't know if you probably memorized the last table, right? So you recognize the numbers? If not, I'll scroll back up to it. Just look at the top line. 3 degrees of freedom for the model, 590, 196, 502. Got them? Let's go back up to the regression. 3 degrees of freedom, 590, 196, 502. So the top part of the ANOVA table is identical. Then you have the same R square and all that stuff, but then you get these two blocks of output. So it did give me the parameter estimates without asking for them. So I was thinking it did in this new version. But you get what are called type 1 sums of squares and type 2 sums of squares that you don't get with the regression output. They don't really help us in this case, but later in the semester we'll do some things where we take advantage of knowing what those sums of squares are. But basically it's partitioning the model sum of squares into the sum of squares for each of the three variables. Right? That we've never seen before. We've partitioned the total sum of squares into model sum of squares, error sum of squares. Well, now we can take the model sum of squares and partition it according to each of the variables. Right? So the sum of these type 1 sums of squares will sum up to 590.4. Right? And you can kind of see that. This is 490. 86 and 12 is about 100. Right? So you're going to get about 590. But if you add them up, they do add up. So it's partitioning it. But down here, these parameter estimates and standard errors are identical to what they were in that regression output. Right? Now, one of the motivations for showing you proc GLM is for the next section, not so much this one, but I was able to get a fit plot. Oh, I know what it was. It was the quadratic model I got the fit plot for. Apparently, you don't get it here because I have more than one x variable. But when in regression you have x and you have x squared, it thinks, oh, that's two variables. I can't do a fit plot. But GLM realizes, oh, that's just one variable. You're just squaring it. So then it gives you the curved model, and you see the fit plot going around the curve. So that's what I was wanting to show you. So here's the quad example that I loaded accidentally a while ago. I'll show you that real quick. That was just to load the data. But if I take this regression and change it to GLM, and put a squared term in there, x1 times x1. So it looks ugly, but it's okay. Then you get that fit plot. Isn't that beautiful? So you fit in a quadratic to it, you get the fit plot. What do you notice about the flaring of the parabola? Right, the confidence bands and the prediction bands, they flare just like for linear, but since it's a parabola, it can kind of make it look like they're wiggling around. They're really not, but it's just that the line is curving as we're trying to flare out, and it makes it look odd. But okay. So now back to this. How do I get? Lost my marker. How do I get a test for this? Where does SAS get the t statistic and the p-value for testing this? How does it get it for testing any of the betas? Okay, you take the parameter estimate, divide by the standard error of the parameter estimate, you get a t statistic, right? So t is equal to B3, which is the estimate of beta 3, divided by the standard error of B3, and that gives you a test statistic, right? And then the p-value, I'll write it in the notation of our calculator, the TCDF function. The main thing I'm interested in is degrees of freedom. So this would be from the absolute value of t up to infinity. So sometimes t is negative. Let me go back to the output that had that negative parameter estimate for beta 3. Oh wait, I'm going to go... right to there. I've got a negative value for my t whenever I have a negative value for parameter estimate. Since it's the ratio of parameter estimate to standard error, and standard error can't be negative. If this is negative, then this is negative. Right? So I could do this by saying t, or I can just always do the same thing and take the absolute value of t to positive infinity, and then you enter degrees of freedom. So what are the degrees of freedom? It says degrees of freedom 1, is that right?
Or is it n?
It's always error degrees of freedom for your t statistics, which is, you were saying it, Kevin, n minus the quantity k plus 1. And k is the number of terms in the model, number of variables in the model, and there's 3 variables in the model, so it's model degrees of freedom. So n minus k plus 1.
So in this case, since there is B1, B2, and B3, K is 3?
K is 3.
Okay.
Yeah, the regression thinks of this interaction term as a whole nother variable. And in terms of matrix way of doing this, what happens to my X matrix when I put this interaction term in the model? What does the X matrix look like? It's got the first column all ones, and then you have your x1, 1, x1, 2, x1, 3, and x1n. And then you have your x2 column, and then, well, I don't want to call it x3. I want to put it what it is. What is x3? X product. Yeah. x1, 1 times x2, 1, and then x1, 2, x2, 2, dot, dot, dot. And that's your X matrix. Okay? So that's the only thing new in section 4.8. Did I say this is 4.8?
Yes.
Yeah, 4.8 is including the interaction term and then testing it. But you need to understand what's the interpretation of that. What am I testing? What is beta 3? Well, it's the change in the slope that I expect when one of the variables changes with respect to the other one. Okay? Change in slope. Okay, so now let's do section 4.9, which is called dummy variables. You're supposed to make jokes about, all right, finally a section for me.
Oh, we were all.
Linear regression cannot be done, simple, or not simple, but multiple regression cannot be done if you have categorical variables. Right? Think about my X matrix. What if one of the variables was what kind of car you drive? Well, how does it, when I take x prime x, I try to do an inverse, that isn't going to work. Right? So regression can only handle numeric variables. Right? But what we can do is sort of trick regression into handling categorical data by creating what we call dummy variables. Right? So to incorporate categorical variables into regression, convert them to 0, 1 variables. So 0 means no, and 1 means yes. So if I have gender, that's a categorical variable. But if I just arbitrarily define female to be 0 and male to be 1, actually males are the ones that are zeros. Right? So. Then I can enter gender, if it's defined with 0 and 1, into my model, and the regression will work just fine. All right? Think about what the parameter estimate would be. If I have gender in my model, let's say I have some other variables, y hat equal beta 0 plus beta 1 x1, let's just use one other so I don't have to write so much, plus beta 2 gender. And I'm just going to write out the name of that variable as gender rather than call it x2, just to keep it straight. Gender only takes on 0 and 1, right? So the interpretation of multiple regression, to get a predicted value, you plug in the values of those variables. So what's my predicted value for females? Good. Beta 0 plus beta 1 x1. So that's the model for females. What's the model for males? Right? So equal beta 0 plus beta 2 quantity plus beta 1 x1. So interpret that for me. What changes between the two models? The intercept. All right? So males and females have the same slope, but different intercept. So like, I'm trying to think of something that's, if my x1 variable was height, right? And I'm trying to predict something based on their height. I don't know. Usually height's what I want to try to predict, but anyway, you might have a different intercept for males and females because males are taller. But the slope is the same. So maybe it's shoe size, right? I'm predicting shoe size. Well, males are taller, so their shoes are going to be bigger. But the rate of change of shoe size per unit change in height is the same, which is probably true, right? The shoes increase at the same rate per inch growth. Yeah?
Does the 0 and 1 also work for adding multiple categorical variables?
That's a great question. He goes, what if I add other, you mean variables that have more than 2 levels?
No, as in like categorical, other categorical variables.
Yes, yes. Let's say I have gender and then I have smoker. Are they smoker or not? I put another variable in here for smoker, add another beta, and it's 0, 1. And then it becomes important to keep track of what's my reference group. And what I mean by reference group is the overall intercept term. Right? So when both gender is 0 and smoker is 0, so I have a female non-smoker. That would be my reference group. Right? So if I plug 0 in for both of those, I'm left with this model. So there's my model for my reference group, which would be female non-smokers. And then I can have male non-smokers, male smokers, and female smokers as a total of 4 different models that I could separate these into. Right? Well, the nice thing about these dummy variables is it allows you to do it all in one model. You don't have to fit 4 separate models. Right? Okay, now what about interaction?
It would just be, I'm still just doing the gender one.
Yeah, let's do the gender one. We said that the intercepts change, but the slopes don't. What if I want to allow for the possibility that not only do they have different intercepts, but they also have different slopes?
It would be beta 0 plus beta 1 x1 plus beta 2 gender plus beta 3 x1 gender.
Good. x1 times gender. Right? So now what would my model for females be?
Beta 1 plus, or beta 0 plus beta 1 x1 plus,
That'd be it. This term is 0 and this term is 0, so they both drop out. So this doesn't change. I still get the same model for my reference group, females. What does the male model do, though?
it would be beta 0 plus beta 1 plus 1, which yeah,
Okay, go ahead.
x1 plus beta 2 plus beta 3x1.
So now, terms with no x's get grouped.
That'd be beta 0 plus beta 2 plus x1 parentheses beta 1 plus beta 3.
Right?
Dr. Moser?
Yep.
So the interaction model, does that work even if there isn't interaction?
That's a good question. Did everybody hear what he asked? He said, does this model work even if there's no interaction? What happens if there's no interaction? Beta 3 is 0. So yeah, it works because that goes away. And then the slopes are the same. Now, in practice, it's never going to be exactly equal. But it'll be a number that's pretty close. Exactly, I didn't finish that sentence. It's never going to be exactly equal to 0. Right, in practice. But we might fail to reject that it's 0 and say, oh, let's take it back out. Then I'm back down to this model. Or it's so close to 0 anyway that it doesn't really affect things. Yeah?
What if the categorical variables are at different levels?
I'll get to that. Okay? Let's take a look at the Da Vinci data, which has male and female. And let's see, I just ran that, didn't I? Yeah. So, and this is Da Vinci data across, I think, all semesters. But let's run, I think it's clear down here at the bottom. There it is. Dummy variable for gender. I did too much in one program. Oh, I don't have it turned on. Okay. So what I've done back, I hate to have to scroll clear back to the top, but I've created a variable. But I do have to scroll up because I don't remember if I called females 0 or 1. Hopefully I called them the same as would. Yep, I did. See where it says if gender equal F, right here. If gender equal F, then gender N, and the N is for numeric. So gender numeric is 0. And that's my own naming convention. You could name it Bob if you wanted to, but I called it gender N. Right? So if gender's F, then gender N is 0. If gender equal M, then gender N is 1. Now I put this line in because I got burned. There are some lines in there where they didn't tell me the gender. And I had an else statement. So if it's female, call it 0. Otherwise, call it 1. And then I got some missing values that got lumped in as male. Right? And they weren't really male. So I left them missing. So if gender is missing, and this is the character SAS version for missing. Quote, quote, with nothing in between. A dot is a numeric missing value in SAS. So if it's missing character string, then numeric missing also. Okay, now page back down to and let's take a look at the plot of it. Now this is actual data, so look at this plot. I got to scroll a little bit so we can see the legend. One of them is males, although it's pretty easy to tell which is which, right? This is the hand length to predict height. So the gender F is the squares, and the gender M are the blue dots, right? Then you have a separate regression. I told it to fit a separate line to each of those types. In the model, what are we going to see happen, do you think, looking at this picture? Is there an effect due to hand length? In other words, is hand a good predictor of height? Well, there's a lot of random noise, but there's a very clear linear trend, right? So I'd say, yeah, there's a main effect of hand. What about gender? Is there a main effect of gender? The blue line is above the black line. That's a main effect of gender. Men are taller, right? What about slopes? Are the slopes the same? They're not different by a huge amount, but the blue line is definitely steeper. What is that telling me intuitively? Hand length and height.
As in gender does not factor that much in like the rate of change.
Okay, if you say they're close to parallel, you say, well, then gender doesn't affect the proportion there, right? But if you think, no, they look like they're different to me, that males is steeper, it means that
A male's hand has a faster rate of change than
okay, and remember, it's the rate of change of height with respect to hand. So height is going up faster as the hand increases for males, right? Which would then tell me that, you know, Da Vinci's 1/9 thing is not quite right. You know, it's a little more than 1/9. Is that the right direction? I don't know. For males, and a little less than 1/9 for females, possibly, right? But that slope is different. The proportion is different. Okay? So now let's run some regression models. Now, I've got a line of code in here that you'll probably see. It says where hand is less than 9.5. There was an influential outlier in this data, so I took it out. It was like that whole scatter of points. There was a hand length that was really tall and way down here. So there was something wrong with that. You know, it's very unlikely that somebody that was that short, and I don't have the plot up here, but somebody who was that short had a hand that was 10 inches long, and nobody else in the data had one longer than 9 inches. All right? So probably the hand length was mismeasured, or the height was mismeasured. So let's look at, let's just look at the plot, or I'm sorry, the regression equation. I'm going to run ODS graphics off here. And then where gender is 1, and I want to run that same thing when gender is 0. So run it first, 0, and then a 1. So everybody see what I'm doing here? I'm running separate lines for males and females. And then let's keep track of them over here on scratch paper. Give me the regression equation. This is this males or females? I have to scroll to see the title. That's male, so that says males also. Oh, I forgot to change the title. I copied and pasted too quick, so they both say males at the top, but one is females and one is males. And so that's what I went back. I actually ran the females first. See where it says and gender equals 0? And then down here it says gender equal 1. Okay, so my output has females first. So the females line is, I'm going to write it here so I don't have to walk that far. Y hat for females. Y hat equals what? Give me the equation of the line. 6.5. Oh, 6.5.
4.66 if you want to round off there.
Yeah, let's go to 3 places, and that's probably enough. So 6.58. Okay, plus
3.943.
3.943 x, right? And that's hand length. And then we'll scroll down and get the males. So males, read it to me. 620. Okay, plus 5.572x. Okay? Now, looking just at these two, would you say that the intercepts are the same or different? I would say different. There's 9 units between them, right? What about slopes? Same or different? Fairly different. Now, how do I do a statistical hypothesis test of whether there's a difference in that?
Just the standard error.
What does... Oh, good. I was hoping I didn't erase it. What parameter measures the change in intercept? What did you say, Kevin? Beta 2. Right? The intercept for females is beta 0. The intercept for males is beta 0 plus beta 2. So in beta 2 is interpreted as the change in intercept. It's how much the intercept changed. What's the change in slope? Beta 3. Went from beta 1 to beta 1 plus beta 3. So I need to test, I need to run the model that has all 3 of these variables in it. The x1 variable, the gender variable, and the x1 times gender variable. And then test beta 2 and beta 3. So let's run that model. Okay, so the overall model, which, well, I don't want to erase that. If we can erase all this. You have to read through this writing. Y hat equal 37.658 plus
minus 9.038 gender.
G for gender.
Okay. Plus 1.629 for H.
Gender times X1 or H, yeah.
Gotcha.
Okay? What do you notice? Look at that compared to these.
It's the last 2.
Now I'm going to turn off the screen so that it's not so cluttered. But
Variables aren't even needed.
this one is that number. Right? So the intercept term, beta 0, right? For both of them. So that's the intercept for the reference group, females. What do you notice about 3.943? Slope for females. So where does negative 9.03? That's how much lower the intercept is. If you take 37.658 and subtract off 9.038, you get that number. What about 1.629? That's the difference in the slope. To get from females to males, you add 1.629. If you add 1.629 to 3.943, you'll get 5.572. Now, let me turn this back on. One last thing before I'm going to let you leave. Are the slopes different? Are the intercepts different? Which one tests what?
The slopes are different. The intercepts aren't different.
Okay.
According to
Gender the gender term in the model, which is the dummy variable, 0.06. So barely not, but not statistically significant change in intercepts. So that you don't have enough evidence intercepts different, although it's darn close. This one tests whether the change in slope is significant. So this says, no, they don't have the same slopes. They have different slopes. Fairly significant, 0.01. Right? Okay, I'm out of time, so I'm still not quite done with that section because you can do dummy variables for categorical variables that have more than 2 categories, right? But that won't be on the test. So the test will only cover dummy variables for like gender or smoke, yes, no, something that only has 2 levels, right? So we will see you Wednesday.